In this video, I'm going to be talking about Lewis dot structures and how we use them to show ionic bonds. Before I get into the details of Lewis dot structures, I just want to say a few things about chemical bonds. Now, atoms, of course, are held together into compounds by chemical bonds. That's why they stick together. And chemical bonds form in order to allow every atom in that compound to access 8 electrons on the valence level, on the outermost energy level. And so we call that the octet rule, that atoms want to have 8 valence electrons. In order to achieve those 8 electrons, metals tend to give up electrons when they form chemical bonds, while nonmetals tend to accept electrons when they form chemical bonds. Now, of course, the noble gases, other than helium, already have 8 electrons, and so they are less likely to want to bond, and that's why your noble gases don't really react with anything else. So ionic bonds are found in ionic compounds. And ionic compounds, you have learned, are formed when a metal and a non-metal atom come together, at least one of each. The atoms that make up this compound are ions, which is why we get the word ionic. It starts with the word ion, because the electrons in these elements have moved in order to form these octets of valence electrons. In general, metals will lose their initial valence electrons. So we have aluminum over here in a Bohr model with our 13 protons. And you'll see that there are 3 energy levels. We have 2 electrons in this first energy level, 8 electrons in the second energy level, and then 1 valence electron in the third energy level. So when the aluminum atom forms a chemical bond, this valence electron leaves. And then the aluminum ion sort of drops back a level, and the second energy level then is its highest energy level, and it has the 8 electrons, so the octet rule is satisfied. Nonmetals, in contrast, tend to gain additional valence electrons to get up to 8. And so we have nitrogen over here, the Bohr model for nitrogen with its 7 protons, and we see in the first energy level we've got 2 electrons. At the second energy level, there's only 5. And 8 is how many the second energy level can hold. So we're missing an electron in 3 places. And when nitrogen forms bonds, it tends to form bonds that gain it those 3 electrons. So now this highest energy level, the valence electrons in nitrogen, is completely filled with 8 electrons, again, fulfilling the octet rule. So ionic compounds, when you're making an ion, a positive and a negative charge, then those atoms are held together by the attractive charges. Opposites attract, just like 2 magnets will attract together, positive and negative charges will attract together. Sodium chloride, a very familiar ionic compound. Well, sodium is going to become a sodium ion when this 1 valence electron in its third energy level leaves and goes and moves over to the chloride ion, or the chlorine atom becomes a chloride ion when it accepts this new electron. So it then has 8 valence electrons in its highest energy level, also a third energy level. And so this is now a positively charged ion. This is a negatively charged ion. And these attractive forces, the opposite charges, will pull those 2 atoms together to form our ionic compound. Now, the ions in an ionic compound actually are giving off their charge in all directions, north, south, east, and west. And so they form what is known as crystal lattices. They don't just stay a sodium chloride, 1 sodium and 1 chloride, but the sodium and the chloride ions just pile up until all of them have been collected to form this larger structure known as a crystal lattice. But the chemical formula we use would just be NaCl, because we have it as the simplest form, or what's known as the empirical formula. So we break it down to its simplest form when we're describing this compound, and the base form would be 1 sodium and 1 chloride. This particular molecule over here, calcium fluoride, its empirical formula is CaF2. So 1 calcium ion with every 2 fluoride ions, which is kind of hard to see from this illustration of the crystal because the fluorides are kind of all mushed in the middle. Incidentally, ionic compounds have some properties that are pretty common across all ionic compounds. They tend to have high melting and boiling points, which means they tend to be solid at ordinary temperatures. They are hard and brittle, and because they contain ions, they will conduct electricity if melted or dissolved in solution, because that heating up to go from solid to liquid or dissolving a solid in an aqueous solution sort of liberates those ions so they can carry the charge. So how do you use the Lewis structures to show an ionic bond? Well, there's a couple of rules you need to follow. First of all, remember your metal cation, your metal ion is going to become positive because it is giving up all of the valence electrons, while the non-metal ion will become negative, will become an anion, because it is gaining electrons until it has filled in an octet in the highest energy level. So the steps to write a Lewis dot structure is to first put the atomic symbol of the atom down on your paper and put square brackets around it. For your positive metal cation, you're going to put the charge outside the bracket plus whatever number, and then eventually you're going to add coefficients to balance the charges. On the non-metal anion, you're going to also start off by writing the atomic symbol and putting square brackets around it. But you're also going to show the valence electrons present around the atomic symbol using the rules that we do for Lewis dot structures, where you have an invisible box and you're putting the electrons on all sides of the box. You're also going to show the charge, which will be a negative charge, and add coefficients as needed. So I'm going to do 2 examples to walk you through this. So the first example, let's think about what happens when we combine magnesium and oxygen to make magnesium oxide. How would we show the Lewis structure? Let's think about these 2 atoms as neutral atoms. So magnesium by itself is in group 2. So that means it has 2 valence electrons, because remember the valence electrons, just using the periodic table, I squeeze all my numbers in here, that the groups 1 and 2 and then 13 through 18, we know from the column how many valence electrons are present. So magnesium has 2 in the neutral atom, and then oxygen has 6 because it's in group 16. So I show my 6 electrons around here. So this is our neutral atom. But of course, we're not doing neutral atoms because this is an ionic compound. So magnesium is going to give away its 2 electrons. So to draw the Lewis structure, we first put magnesium again and put square brackets around it. Because it's giving away 2 electrons, this means there'll end up being 2 more protons than electrons. It's going to have a positive 2 charge. And oxygen is going to accept those electrons when the chemical bond is formed. So to the 6 electrons that are happening naturally in oxygen, we're going to add those 2 from the magnesium. So at the end result, oxygen has added 2 electrons beyond what it has normally, and so it has a negative 2 charge. And so our positive 2 charge and our negative 2 charge will pull these 2 ions together and form our magnesium oxide, MgO, compound. And to draw the Lewis structure, you're going to just have this formulation here showing the atomic symbols in square brackets and then the charges above it. Remember to show all the valence electrons for your nonmetal, for your negative ion. And you don't have to use different colors. I was just trying to make it clear where those electrons were coming from. How about calcium and bromine to form calcium bromide? So again, calcium's over here in group 2. So calcium as a neutral atom is going to have 2 electrons. Bromine is way over here in group 17. And so it as a neutral atom is going to have 7 electrons. It only needs 1 more to make the 8 valence electrons an octet. So calcium is going to give up its 2 electrons, and that will turn calcium into a positive 2 ion, just like we just did with magnesium. And that those electrons are going to be picked up by our bromine to turn into a bromide ion. But each bromide ion by itself only has a -1 charge because we've only added 1 electron from the calcium. So in order to balance this equation, we're actually going to need 2 bromide ions. And so we need to put a large number 2 as a coefficient as compared to a small superscript number telling us our charge when we write the Lewis structure. So again, for calcium bromide, the standard formula would be CaBr2, but the Lewis dot structure is going to show the using square brackets around your atomic symbols, show the charges, and then add a coefficient as needed. Again, don't forget to show all those 8 valence electrons around the nonmetal. So that's the process of using Lewis dot structures to show ionic bonds. It may seem complicated right now, but after you've practiced it a few times, I think you'll see it's pretty straightforward.